Hi everyone, my name is Leela, and over the summer I've been working with Professor Paley's group to help their robotic fish imitate two behaviors that we see in biological fish. The first being schooling, and the second being what's called intermittent locomotion, which just means that instead of a fish beating its tail continuously side to side, it's going to thrust and steer in a burst phase, and then glide and sense its environment in a coast phase. We'd like to imitate this behavior in part because it's often more energy efficient than continuous swimming. And so if you're a small fish robot with a small energy budget to match, that sounds pretty good to you. Schooling can also help with energy efficiency, but another reason we're interested in it is that it could be a step along the way to doing more complex things with the fish. Plus it has a few applications of its own. So when we say that we'd like to imitate schooling, what exactly does that mean that we're trying to do? If you look at this picture of schooling fish, you might notice that they're packed in there pretty tightly and that they're all swimming in the same direction. And it's that second piece of the puzzle that we've been working on this summer, which really cut down on our work because it meant that we could describe the entire abstract state of our swarm of N fish with just N angular variables. Whereas if we'd included relative spacing, we probably would have had to deal with positions and speeds as well. But with just the headings, we could state our goal as driving those N headings to a single consensus value. And the good news, if that's your goal, is that a lot of people have worked on similar projects in the past. So for example, there are already several tried and true approaches to getting N angular variables to coincide, but most of them require some modification in order to be compatible with intermittent swimmers like ours. On the other hand, my research mentor at UMD, Mr. Thompson, has been working with a single intermittent swimmer and has figured out a way to drive it to a desired heading, but we'd like to be working with more than one fish at a time. So much of the challenge for this summer was to see if we could combine these two strands of previous work in order to build a controller that would drive a full swarm of N fish, each of which was an intermittent swimmer, to a consensus heading. And here's the controller we came up with to do that, which I know is an explosion of symbols, so let's take a quick tour. During the burst phase, which you might remember is when all of the steering is happening, the rate of change of our cave fish's heading is going to be given by our steering input that we feed the fish, plus we know there's going to be some actuation noise. This theta hat ki is the cave fish's estimate of the ith fish's heading relative to it. And those estimates are all going to update during the coast phase according to this fourth equation over here. Just to get a feel for it, you can see that the rate of change of the fish k's relative estimate, fish k's estimate of fish j's relative heading is going to be proportional to the true relative heading minus k's estimate of the relative heading. Plus, we know there's going to be some sensor noise. So these are the system dynamics under our controller. And once we had these equations, our next step was to see, okay, can we find conditions on the gains K and L and the duty cycle given by B and T, under which the fish are all driven to a single consensus heading? The answer we found was that in the absence of noise, if this inequality is satisfied, the fish will all be driven to a consensus heading. But of course, we know in the real world there's going to be noise. And so we then went back and derived approximate bounds on the convergence value of the maximum heading difference between any two fish in our swarm in the presence of noise. So at this point, we have our model for the system dynamics under our heading controller. And we have some theoretical predictions based on our analysis of that model. So our next step was to test those predictions with MATLAB simulations. You can see some of the figures generated in those simulations on the right side of the screen. So in this run, we set the model parameters so that this inequality was satisfied. In the second run, the inequality is not satisfied. And you can see that only in the first run do the headings of all the different fish converge to a narrow band and then stay that way for the rest of the trial. Whereas in the second run, where the inequality is not satisfied, the headings are going all over the place, not even close to being in agreement. So what we found on MATLAB simulations matched what we expected from the math. Okay, that's some of the progress we've made this summer. And if there are any questions, I'd be happy to try to take them now.